In this video, we are going to explore logarithmic functions. We're going to go from logarithmic to exponential and from exponential back to logarithmic forms. We're going to evaluate logarithms. We're going to use the common and natural logarithms. We'll always just say log, but it's actually logarithms. Anyways, so we're going to first start with some rules of exponents that you would have learned in a previous math course. And if I look at my first example here, this is going to be x to the third, y to the sixth. And the reason that is if I have a, b raised to some n power, over multiplication and division, that power is going to be distributed on both the a and the b as an exponent. And then furthering this, suppose I have a to the m, b to the n, and I have it to the p power. Because it is a power-to-power rule, this becomes a to the mp, b to the np. On the next one, since we already talked about how this is going to distribute, if I have a to the m, b to the n raised to the p power, it distributes over multiplication and division. So this is a to the mp divided by b to the np. So similarly, this would be a to the 15th divided by b to the 10th. When we have like bases, such as this, when we're doing a to the m multiplied by a to the n, we add and subtract like bases. So in this case, this would be y to the 3 plus 4 minus 2, which is y to the 5th. And since we are adding exponents when their bases are the same, when we are dividing bases that are the same, we are subtracting exponents. So if I have a to the m divided by a to the n, this becomes a to the m minus n, or it's 1 over a to the n minus m. It just depends on which one is the higher power in terms of how you're going to subtract. So if the higher power is in the denominator, such as this c, I'm going to subtract down. And in a and b, I'm going to subtract up. So this is going to be a to the 1 minus a negative 4, because it's negative 4 in the denominator. I'm going to have b to the 4 minus 2. And then I'm going to subtract down, so I'm going to have it c minus 1. So I'm going to have a to the 5th, b to the 2, and c to the 6th, and that's my final answer. Now the reason we're covering this is because exponentials have the exponent as the variable, and logarithmic functions is the inverse of an exponential, which means with logarithmic functions, the rules of exponents will apply because the logs are just basically exponents in disguise. So here's how we go from an exponential to a logarithmic and from a logarithmic to an exponential, because they are inverses of each other. So if I have base b to the y, the answer is x. And the way that I would write the inverse of that is the log base b of x is equal to y. So if you want to think about this, a log base b of x is equal to y. This is the base raised to the exponent equals this. So b to the y is equal to x. Then the easiest way to think about how do you go back to a log, well, if you notice how we say log base b, since this is base b, we know that is where that will go. Log base b of x is equal to y. So base b of y is equal to x. So b is the base of the log. Y is the answer, and x is what we're taking the log of. Because logs and exponentials are inverses of each other, we know that their domains and ranges will become what we had, but with the switched position. Because remember, when we solve for the variable x, when we're doing an inverse, it is at that moment when we solve for x and switch x with f inverse of x, and y with x is when the domains and ranges switch positions. So we could say that this would have been the range of the exponential, And we would have said this would have been the domain of the exponential, which we know now is the domain of the log is the range of the exponent. The range of the log is the domain of the exponent. We have a couple of rules we're going to start implementing, which is always going to be true, is that if I have the log based a, so the log of any base is equal to 1, log base isn't equal to 1. The log of any base of 1 is always equal to 0, and the log based a of anything of itself is 1. And this makes sense, because if I return this into its equivalent exponent, it'll be a raised to the 0. A raised to the 0 is equal to 1, and that's true all day long. And a raised to the 1, a raised to the 1 is equal to that a, just like that's equal to that 1. So when we look at exponentials and logarithmics, because they are inverses of each other, that we still have for the base a being bigger than 1, it'll be increasing. And if we have a base a of the log, it's going to be increasing. They would, of course, be symmetric over the line y is equal to x. So this point right here becomes this point down here. And this point right here would become this point right here, because x's become y's, y's become x's. In the exponential, we have no x-intercept, and so for the logarithmic, we have no y-intercept without transformations. So you can see that they are true inverses of each other based on what we know about inverses. We have the common log. So if you look on your calculators, you have a log and you also have natural log. So there are two things that you have, which is the common log and then the natural log. So first we'll talk about the common log. When we have a base 10, because it happens so frequently in nature, log base 10, we just write log. So on your calculator, this is the log base 10, and we call it the common log. And using the fact that log base 10 of x is equal to y means that 10 to the y is equal to x. So that's the common log. And we have the ability to put any of this stuff in our calculators. So get your calculators out and put these in your calculators. So pause it now and put this in your calculator. And what I got, I'm going to round to 4 decimal places, is the first one I have 5.8101, 4 decimal places. The common log of 0.0009, let me put that in my calculator. Oh, I need to get my glasses on. That was my pen I just dropped. Make sure I have enough zeros. Okay, and it looks like I do. And this in my calculator is negative 4.6216. And then if you were to try to do the log of negative 3, you're going to get, if your calculator allows you to, you're going to get a complex number. And you're like, what just happened? Well, remember that the domain of the log based b of x is 0 to infinity, not inclusive of 0. So sure, our advanced calculators will give us an answer, but it'll be in a complex form. It'll have an I in it. And we don't do that in this class. So we would say that this is not in the domain. If you don't have a fancy calculator that gives you the answer in complex, then it's going to say domain error, which makes sense. The other log that is special to us that's on our calculators is the natural log. And I talked about that just a moment ago. We have e, the number e. So the log-based e of x gets reduced down to ln of x. So ln of 1 is 0, and that's because, again, the ln of 1 is the log-based e of 1, which is 0, and turning it back into its exponential, e to the 0 is equal to 1. Now, e is a number, and what that number is about 2.72. E is approximately 2.72. And it's there's a definition for it that we go into in Calculus 2. We actually define it in Calculus 2 formally, and we Actually, you would define it in Calculus 1 as well. So it is approximately 2.72. Now this, without doing any work here, I don't have to do this in my calculator because I know that -5 is not in the domain of the log. So I'm not even going to bother that one. And when I have ln of 1, I know this is 0, and the ln of e is 1 because this is the log-based e of e, which is equal to 1. So the only ones I actually have to put in my calculator, and then pause this now if you'd like, is I'm going to do the natural log of 645,778, which I get to be 13.3782. And then I'm going to do the natural log of 0.0000239. And I get -10.616. 4, there's a 4 in there, 416. There we go. So we have these on our calculators. Nice, easy peasy. Make sure you know how to use not log and natural log, and know when you can't use it because of a domain issue. So if I'm asked to convert from a log to an exponential, I know it as 4 raised to the t. 4 raised to the t is equal to 7. And this is the common log, so this is going to be 10 raised to the 0.845 is equal to 7. And you can confirm this with your calculator. Like you can do 10 raised to the 0.845 and it should give you 7, well, approximately 7. This is, remember, this is the log-based e, so it is e raised to the -0.9676 is equal to 0.38. And then this last one, e to the t, is equal to w to the 5th. And so that's how we convert from logs into exponentials. And then for these, I want to solve by converting into an exponential form. So what would the x be? Well, this is 5 squared is equal to x. That means x must be 25. 18 to the 2 must be equal to x. And that's not one I can do in my head, so I'm going to have to do 18 squared, which is 324. And then e to the 2 is equal to x, and I can just leave it just like that. Now I'm going to use the definitions of common log and natural logs to simplify. Now right now I don't have anything here, so I'm going to put these as y just to make my life easy. I'll talk about that last one in a minute. So I'm going to have 10 to the y is equal to 100 to the 8th, but 100 to the 8th is 10 squared to the 8th, which is just 10 to the 16, so y is equal to 16. So I'm going to do, on this one, I'm going to do divide both sides by 2 first, so I have the log of 0.01. Let me do this in another color so it doesn't get mixed up with the one I just did. So I'm going to come over here. So I'm going to divide both sides by 2, and so I'm going to have the log of 0.001. I think I have another 0, right? One more 0 is equal to y divided by 2. So 10y divided by 2 is equal to 10. Actually, I'm not ready to talk about that yet. Is equal to 0.00001. But 10 to the y divided by 2, 0.0001 is 1 divided by 1, 10, 100,000, 10,000? Let me see. Yes. Because it's tens, hundreds, thousands, 10,000s. Okay. But this is just 1 divided by 10 to the 3rd, which is just 10 to the -3. So y divided by 2 is equal to -3, so y is equal to -6. Rules of exponents. That's all I'm doing at this point. This one is easy. This is the log-based e. So e to the y is equal to e to the -5.03. That means y is equal to negative 5.03. Now for D, I'm going to take this first term right here, and I'm going to put it into its exponential, equivalent exponential, or excuse me, equivalent logarithmic. So do this in black. So this is the log based e of y is equal to the natural log of 10.125. However, the log based e is just the natural log of y is equal to the natural log of 10.125. And this is only true when this and this are equivalent, right? That's the only time it's true. So when I see this, the e raised to the log based e, it is just simply going to be whatever this value is. So this is going to be equal to 10.125 plus 4, which is 14.125. So here's another thing you can put in your toolkit of knowledge. If you have b raised to the log based b of x, this is equal to x all day long. So you want to make sure that you write that down somewhere and remember it. All right, so what I'm going to do again is I'm going to set each one of these equal to y and do the same thing like I just did without using a calculator. 3 to the y is 1 over 27, but 1 over 27 is 1 over 3 cubed, which is the same thing as 3 raised to the negative 3. And this only happens when this exponent equals this exponent, just like up here. This only happens when this exponent equals this exponent. So that means y, that's terrible, don't know what that was. That means that y has to equal negative 3. This one is 10 to the y is equal to 0.001, but 0.001, tens, hundreds, thousand, this is 1 over 1,000, which is 1 over 10 cubed, which is 10 raised to the negative 3. So y is also equal to negative 3 on that one. This one I'm going to divide both sides by 25, so I have the natural log of e to the 2/5 is equal to y over 25, equal to y over 25. Don't know why I try to do that as an exponent. I'm not ready for that. Y over 25. So converting this back here, this is, let me rewrite this down here. This is the log based e of e to the 2/5 is equal to y over 25. That means e, turning this to an equivalent exponential, e to the y over 25 is equal to e to the 2 over 5. That means y over 25 must be equal to 2 over 5. That means y, multiplying both sides by 25, is going to give me 10, because 2 times 25 is 50 divided by 5 is 10. And then I'm going to do something similar here. Is I'm going to go ahead and divide both sides by 6. So the log of 8 of 4 is equal to y divided by 6. So 8 y to the 6th is equal to 4. And then for this one, what I'm going to do, let me just erase all of this, is I'm going to get them to a common base. So I know 8 is 2 raised to the 3rd and 4 is 2 squared. So I'm going to rewrite this as 2 to the 3rd, because that's what 8 is, y over 6, is equal to 2 to the 4th. Now I'm going to go ahead and do the power to power rule, in other words, multiply those two, and I get 2 to the 3y over 6 is equal to 2 to the 4. But 3y over 6 is 1/2, and I wrote 6. That's pretty spectacular. So 1/2, which is equal y times 1/2, or y over 2, which is equal to 2. Good morning. This is a 2, and this is 2, because 4 is 2 squared. 2 squared is equal to 2, so y is equal to 4 by multiplying both sides by 2. Okay, there are total, complete reasons why we learn logs and exponentials, and one of the reasons that we learn logs and exponentials is because earthquake magnitude decay of radioactive material, pH in chemistry, loudness is all done with logs or exponentials. So there's a lot of real-life applications for logs and exponentials, which means if there's real-life applications, we have to be able to do the math behind it. And that's what we're doing now, is the math behind it, so that if you go into your field and you have to talk about exponential growth or exponential decay or pH in chemistry or earthquake magnitude or the decibels for loudness, advertising responses, all of this stuff can be modeled in exponentials or logs. So if we take a look at this example, and it says, students in an accounting class took a final exam, and then they took an equivalent forms of the exam at monthly intervals thereafter they took their accounting class. The average student score S of T as a percent after, that should be after, not aft, after T months, right here, after T months was found to be given by this function. What does a 78 represent in this function? Well, if I were to put in 0, so S, actually it's not a lowercase, it's a capital. I'm going to make my S's as a capital like that, S of 0, because otherwise my S's look like 5s. So S of 0 would be equal to 78 minus 15, and then I'd have the log of 0 plus 1. So this would be 78 minus 15, the log of 1. But we know the log of 1 is 0, so this equals 78. So that tells me that this is the initial average for the final exam. And then what is the average score after 4 months and 2 years? So then since T is in months, so I would do first 4. So I'd get 78 minus 15, the log of 4 plus 1, and I'd put that in my calculator. And then I would do the S of 24 months, which is 2 years, and 78 minus 15, the log of 24 plus 1, and then whatever that is in your calculator. And that's it for this video. Not too bad. And we'll see you in class.